next 60 to 90 minutes, we'll go through 4 of our most popular workflow solutions. For example, with the solver and specifier, you can exercise a lot of control over the simulator. Solvers act a bit like feedback controllers, more on this in a bit, while specifiers act a bit more like feed-forward controllers. If you have a bunch of case studies you have to do, we have an automation tool called the scenario tool. And if you have user values like your own variables and properties and correlations you want to put into ProMax, but you don't want them separate in a different flow sheet or a different Excel file, you can use our user value sets. So let's start with the solver. I'm going to explain how it works, I'm going to use a real-life analogy. So as you can see here, we have a cold process fluid that we're trying to heat up to a certain value. So we're trying to set the temperature of the hot process fluid. In real life, how you would do this is to use steam or any sort of heating fluid. However, to control the temperature of the hot process fluid, you need some sort of measurement. So in this case, we measure the hot process fluid's temperature, and then we compare it to a set point. The set point is just what target temperature you want it to be. And then this will come up with an error. So how far you are from your goal. And then a PI controller takes this error to figure out what kind of corrective action to do. It then does create some corrective action in the steam flow rate. And this corrective action will in turn affect the process fluid's temperature, generating a new error. And this loop continues on until your error is 0. This is a lot like how a ProMax solver works. It takes an error function, and then it just adjusts some sort of corrective action until the error reaches 0. The main difference between a ProMax solver and a PI controller, for example, is that it can use a lot more advanced algorithms to get to your target very quickly because it doesn't have to worry a lot about the system dynamics. In contrast, let's look at how a specifier works. It actually works very similar to a feed-forward controller. How does a feed-forward controller work? Well, it first measures an independent variable. It's not called the measured variable, it's called independent because it is independent to whatever you're controlling. So if I were to change my steam flow rate, no matter how much I change it, the cold process fluid coming into the heat exchanger will have its properties constant. It doesn't affect it one or the other. A feed-forward controller then uses some information to create proactive action. So this one is ahead of, before it even starts getting heated up, it already creates the action for you. So how does it do it? Instead of using intelligent trial and error until you hit 0 error, you need some sort of knowledge of the system. And this coalesces in some mathematical relationship. For example, maybe you did a bunch of tests on ProMax and found that on average, you need to use about 5 kg of steam per meter cube of process fluid for heating it up 20 Celsius, for example. With this information, what you can do is you can measure the flow of your cold process fluid and then use this information to calculate how much steam you need to achieve your goal. This whole thing is very similar to how a ProMax specifier operates. It takes one or more independent variables, uses some mathematical relationship you give it to apply this proactive action. One of the biggest questions we get especially when we do face-to-face trainings is what's the difference between a specifier and solver, and when should I use which? I hope previously my explanation was a bit clear on how it works, and I'll be reinforcing it with this table and some examples of when to use which. We have already shown the real-life equivalents to the specifier and solver. that being the feed-forward controller for the specifier and the feedback controller for the solver. I've also shown you the main inputs, independent variables for specifier, and it uses some sort of knowledge to create proactive action, whereas a measured variable for solver, and it uses an intelligent guess and check system to bring the error to zero with reactive action. The main advantage of using a specifier is its speed. Since it's proactive, it doesn't need to guess. It just takes whatever information, does some math, and it gives you the results straight away. So there's no iterations required or anything. In contrast, a solver is using guess and check. So it has to at least guess once and check once. And if the value is not that quite there, it will guess and check again and again and again. And you'll iterate before I can get the solution. However, this speed comes at a price because the specifier needs a lot more input than what a solver might need. A specifier needs some mathematical relationship between the desired outcome and your independent variable. If the relationship is too complex, like if it requires an integrator or ODE solver to work out, then you're probably better off using a solver. Additionally, if your mathematical relationship takes too many assumptions or has too many exploitable blind spots, then you should really be considering using a robust solver instead. So, as a rule of thumb, we recommend you use a specifier unless you lack a good rule of thumb or design guidance. What do I mean by this? Well, let me show you some examples using this simplified amine unit. It just takes a bunch of sour gas to turn into sweet gas by taking lean amine and circulating it, washing the acid gas down. We have covered a lot of these rules of thumb during our amine sweetening webinar a while ago. First, what if my goal is to put enough pressure into the lean amine so that it can enter the absorber? Okay, this is quite direct. I wouldn't even consider it a rule of thumb. It's just a bit of common sense. I'll take the top pressure, add a little bit, maybe half a bar, and that should be enough to push the liquid in. This is a very good case to use a specifier because it's direct, it's simple, and it is very robust. And by doing this, if you were to do any case studies or maybe your sour feed has different pressures, you will be able to automatically tune the pump's pressure so that it will, no matter what it is, it will always be able to push the lean amine into the column. What about something less direct? What if I want to prevent hydrocarbon condensation while maximizing absorption? We've covered this a bit during our amine sweetening webinar, where the colder it is, the better it is for absorption. But if you put it too cold, you will start to have hydrocarbon condensation, which is not ideal. I would like to request everyone mute your mics, please. Okay. So, moving on. A rule of thumb covered during our amine webinar is you want your feed temperature of your you want the temperature of your lean amine to be your feed temperature plus 5 degrees Celsius. This will guarantee you will not have any cooling, therefore no condensation going down. This is an indirect use of a mathematical relationship, but it's also a very good case to use a specifier because the relationship is simple. While it's not direct, you still get your goal with a safe margin. But when you are dealing with indirect specifiers like this, it's important to understand the assumptions and applicability of the mathematical relationship you are using. The sour feed was just H2S and CO2. There would be no hydrocarbon in it, so there's no risk of hydrocarbon condensation. So you don't really have to apply this rule of thumb anymore. Okay, Last one. What if I want to maximize amine loading? So if I'm using MDEA like I am here, one rule of thumb is to say that the maximum amine loading is 0.5 moles of acid gas per mole of amine. In theory, you can use this number. You can use this number, figure out how many moles of acid gas is coming into your feed, divide it by 0.5, and that will give you your molar flow rate of the amine required. While this seems useful, it has a lot of assumptions and blind spots. The biggest one is that it does not consider how much unabsorbed gas you're taking because it assumes everything is absorbed. This is not true all the time. And as a result, if you use a specifier for this, it will not be as robust if, for example, your column is not sized big enough to absorb everything. This is a very good case where you want to use a solver instead, because you don't have to worry about all the complex mathematical relationship between how much unabsorbed acid gas it is, because the ProMax model will deal for you. So you can use a solver. It might take a bit longer, but it will give you a correct answer and let ProMax do all the hard work for you. Okay. The next section, I'll keep very brief because we'll be going through a lot of this during our demonstration. It's intended more as a way for you to review it after the webinar. So let's start with the specifier. Some of the things you can put in are the name, for example. You want to help yourself differentiate the different solvers and specifiers you have. And okay, you can add as many independent variables as you want through this add button over here. And anything you add will come up under this list, independent variables, where it will have their name, the given name you gave it, its value, as well as any units that are associated with that value. Then you put in that mathematical relationship I've been constantly talking about into that box there. And this is very useful when you have more complex ones that involve if then else statements, where you can click on this check error button and we will check for any syntax errors so you can make sure everything you typed in makes sense to the computer. A simple solver has a very similar look to it. However, as we discussed, it's still fundamentally different from a specifier. It has all these the usual suspects with the specifier. You can put in the name, you can add measured variables and check any error the same way. The main difference is this part. You do not put in a mathematical relationship. However, instead you put in an error function. This error function, the most common one is just taking your measured variable minus whatever target you want it to be. By default, convergence happens when the number over here reaches below 1 times 10 to the power of -3. You can have, we have some options if you want to bounce between solvers or test certain things and you want to activate or disable or swap solvers using ignored. And if you have multiple solvers, you can elevate some of them to be more important than others through weighting, where higher weightages means it will take more iterations to get a more precise answer. Or you can force them to solve in a certain order by setting priorities. ProMax will automatically solve from high to low priority, and it's generally faster to give higher priorities to upstream units versus downstream, and faster than slower solvers. I'll be showing this a bit more during the demonstration, which I will start now. As usual, if you have any questions throughout this process, please post them in the To Everyone chat, and our helpers will help you. Okay. So this is a brief example file of an amine sweetening unit that uses MDEA. A brief run through, sour feed comes in, gets sweetened and comes out as sweet gas with low H2S and CO2. The amine goes through this loop where it absorbs, flashes, preheats, goes to a regenerator to remove acid gas, and recycles back in. It is currently not meeting its specifications of 8 ppm H2S and 0.45 rich loading. These rules of thumbs were again covered during our amine sweetening webinar. So before we play around with the numbers, we want to make our life easier to do that. So one of the things that one might do to fix this amine rich loading is to change the lean amine flow rate. So you want to increase the flow rate to reduce. You want to increase the flow rate to reduce the rich loading. However, when you increase the flow rate, suddenly this steam flow rate that is fixed will be too little. So I don't want to have to change two numbers at once. I just want to change one number and that's it. So let me link the two using a specifier. So I'm going to go into my steam tubes, double click on that. And I'm going to go to the mass flow and right click it and go to create simple specifier. When I click on that, a new window will pop up. And the very first thing I want to do is give it a name. I'm going to name it steam flow specifier. Okay. And then the mathematical relationship I'm going to use is my amine flow times 130. This value, 130, we covered during our amine sweetening webinar, where this is the range of steam ratios we want to use, where 130 refers to 130 kilograms of steam per meter cube of amine flow. So how does ProMax know what this amine flow means? Well, we have to tell it by adding an independent variable. Okay. So we click on add over here and it brings up a property tree. We can navigate through the tree to narrow down where specifically it is. So I'm gonna click on this plus over here. It is a flow sheet. The flow sheet is called MDEA unit. And I'm looking at a P stream. P stream just means process stream. And in our case, we're looking at the stream called made up lean amine. We are only interested in the total phase, and we are looking at a property. And the property we're looking at is standard liquid volumetric flow. I'm going to give it a name. You have to be very careful with this. Make sure it is case sensitive, and it must be exactly what you have in the mathematical relationship. So I'm going to give the exact same name, amine flow. I click on add. Straight away, you will see the number comes up here. It is currently 45 meter cubes per hour. And when you multiply it by 130, you get about 5.8 kilograms per hour. Doing this will make it so anytime I make any changes to the amine flow, I will automatically get an appropriate amount of steam flow rate. Remember, this is actually an indirect specifier. Reason why it's indirect is because the goal of this specifier is to make sure I have enough steam to clean up the amine. So this number, 130 kilograms per meter cube, is specifically for fully loaded MDEA. So if your loading is small, like if you have you only expect like 0.1 in an AGE, you wouldn't use this much steam. Okay. Now that I've done, I can re-execute the project. And now whenever I make changes to the lean amine flow, my steam flow rate will automatically adjust itself. So Let's take a bit, look at the results, and then regroup and see what else has to be done. Looks like it converged. And my new acid gas loading is roughly the same, but my H2S dropped a bit. Not quite to what we need, but it dropped a bit. So it is inevitable that we have to increase our amine flow rate. But instead of doing this manually, where I do the gas and check, I want ProMax to do the gas and check for me. So I can set up a solver to do this. I'll double click into this stream and look at the standard liquid volumetric flow rate. I want this to be adjusted, so I'll put a solver in it. I'll give the solver a name, amine flow solver. And over here, you want to put in an error function. So the error function in this case is what I want to measure. So I'm measuring the rich loading. And I deduct the target, 0.45. That's my target rich loading. Okay. So how does ProMax know what your rich loading is? Well, I've shown you one way of specifying it, where you go through the tree. A more convenient way for some is to just pick up that information from the stream itself. So where is this rich loading found? It's found under rich amine. I'll double click that. Under analyses, you can see here the total acid gas loading, 0.545. This is the number I want. So I'll right click on it and copy its moniker to clipboard. A moniker just means its address in terms of ProMax speak. After I copied it to my clipboard, I can use this project viewer like a Internet Explorer or any website browser. I can click on back and you bring me back to where I was last, my amine flow solver. Now, when I add, instead of looking through the tree, I can now click on clipboard. And this will show me exactly where this is located. And I'll name this rich loading. Click on add. And you see the rich loading that I had before, 0.545, is now here. Okay. Before we move on, there are actually two solvers in this flowsheet. If you are ever unsure of how many solvers or which order they solve, on the left here, you can scroll down and find what we call the solver summary. Double click on that. You'll see we have two things. First thing, recycle block. Second thing, amine flow solver. This is the thing we just created. So remember the rule of thumb before? I said you want to give higher priority to faster solvers. But what do I mean by faster? Let's consider the calculation path for both of these. Let's start with the amine flow solver. The amine flow solver will start from this stream, solve 1 block, 2 block, 3 block, and then it will get me my rich amine rich loading, and then it will make another iteration. So it takes 3 block solves before I can make a single iteration. What's my other thing? The recycle block, because it actually has to make sure this matches this stream. So in order to do that, it has to solve 1 block, 2 block, 3, 4, 5, 6, and I consider the whole regenerator as 7th block. Solving 7 block is twice as slow as solving just 3. So logically speaking, in order to optimize how fast it converges, I want to give my amine flow solver a higher priority. I can give it 2 and it will automatically move up, or I can give it 100. It does not matter as long as the number is higher than the other number. Keep in mind, I'm just going to solve this right now for you to see. And you can see from this how it works. It goes green all the way here, and then it'll stop, and then it'll go back, make another iteration, and it bounce through this until this error drops below a certain amount before it will even start to consider the recycle block. And once it makes one iteration in recycle block, it redoes everything from the amine flow solver. One thing to keep in mind with this is the priority does not affect the end result. So if you have all the time in the world to burn, you don't have to worry about this priority at all. All it does is to get you to that result faster. And as usual, if you ever have a huge file with 10s, 20, 30 solvers, please do not worry too much. Please do not worry too much. You can you can email us the file and we can optimize it for you. Okay. I see someone asked that. Repeat that again. I'm just gonna say, don't worry about the priority too much if you have a lot of time. But if you want the solver to get the answers quicker, you will want to optimize the priority such that your faster solvers have higher priority. Okay. Next, if you ever want to specify the maximum number of iterations, it's actually right here. So in this case, I only allow them 20 iterations before it starts to give up. Okay. So now that I have this solver set up, you will notice that in this callout, it has now a pound symbol, or some people call it the hashtag symbol. And what this symbol just means is it's specified somewhere else, but it is a specified object. Something like this without any symbol just means it is calculated by ProMax. So the rich loading is calculated by ProMax. Okay. So now you can see with our solver and specifier, this automatically changes to get me 0.45 total acid gas loading. And I just so happens I hit my H2S target. And my steam tubes automatically update with how much steam I need to clean this new flow rate. So doing this makes it so you don't really have to do any manual work. You just set it up once. And now anytime I do changes to my sour feed or any other system, it will automatically solve for those conditions and make sure we hit our targets. Okay. So now that's done. Let me go back to my presentation and cover the second, well, technically the third important tool, which is the scenario tool. Okay. Imagine we have that exact same ProMax model, but instead of a design, this is a model of a relatively new plant. Now, your supervisor asks you, when should I top up the MDEA? Well, in this particular model, we have a constant makeup stream that feeds in small amounts of MDEA to make up anything lost. But in reality, you don't have a small pipe feeding small amounts of amine constantly. You just periodically dump a bunch of it. And so as you lose amine, your MDA strength actually drops. And what lower strength means is higher loading, worse H2S capture, and you are tasked to determine at which point does it start to become unacceptable. How you would do this is probably set up a table on Excel. You put in a bunch of tests you want to do, maybe start with 50, your baseline, then drop it down all the way to 40. And then what you're interested in is maybe something like the H2S, how much H2S it is, because you expect this to increase. Well, ProMax has a handy tool called the scenario tool. And this automates this whole process. So you just have to set it up once and you can run as many scenarios as you like. And it's all automated. It will take that input one by one and put it into ProMax. We'll run the ProMax model and grab all the input outputs you're interested in back into that same Excel table. It will do this one by one automatically, and it does not require your supervision at all, which means if you have a huge study to do, maybe 100 different studies, you can just leave it on overnight or leave it on during lunch. And by the time you get back to your desk, you can see most of the answers along the way. This next part, again, I'll keep brief because I'll be going through a lot of this in the demo. But this is more for you to revise because we'll be sending these slides out to everyone after the webinar. Okay. Because we allow you to set up multiple different scenarios for the same ProMax file, make sure you name them, because if you don't, you might not remember what each one was a few weeks later. This area is where we deal with ProMax inputs, which means stuff we take from Excel and put into ProMax. And this area, we look at ProMax outputs, which means we take from ProMax and put into Excel. You have a lot of control over what you're running because we can, for example, if we have 100 different runs, maybe we are only interested in run number 50, we can just use that. And for each input and output, we have a dialog box that has 4 main things you need to input. The first thing, and probably the most important thing, is the name. Because if you don't know what it is, you probably won't remember it in a bit. So it helps you differentiate different variables for future reference. The second thing is the ProMax object. It tells the tool where on ProMax you want to grab or input data. So you can navigate the tree or copy and paste the moniker. We'll show this off during the demonstration in a bit. The next most important thing is the cell address. Where do you want to put this or grab this information from Excel? And the last and the thing that I would say is quite useful as a sanity check is the units. You want to make sure you have the correct units that is being grabbed and input into ProMax. And this acts as a sanity check because if you intend to put mass flow rate and you see kilomoles per hour here, you know something's up and you should double check your work. Okay, so let's move on to the demo. Okay, so before we start our scenario 2, there is one very important thing we have to do. This is technically an existing plant. So I cannot change this flow rate because it is somewhat fixed based on how big the pump is. So to do that, I'm gonna go into the solver. I'm going to click disable. What disabled means is this solver will no longer run. So whatever number I have here, 56.9 meter cube per hour, will be fixed for the duration of the study. You can leave this on if you wanted to study something else, but in our case, it makes more sense to leave it off because we are limited by how much flow we have in our pump, as well as the size of our reboiler, how much steam it can even take. So by disabling it, these two numbers will more or less stay fixed throughout the whole study. So recall that I said you have some table in Excel. You could use your own Excel file with your own table and attach our scenario tool on it. But a more useful tool we have is this button right here, Add Excel Workbook. It will embed a workbook into ProMax, which means every time you open it, as you see below here, a workbook, Excel workbook will be attached to it. Why this is very useful is because sometimes you don't want 2 different files that are the same thing to be separated. This will make sure all your information is neatly packaged into a single file. I pre-prepared a table of what I want to study, as well as a little graph that will slowly generate as we move along. So in this case, I'm doing the same study I explained before. I only have one input, take my MDA weight percent and drop it down. And I have 2 outputs. I want to look at the 2 specifications I'm looking at. Sweet gas H2S and rich loading. Okay. To access the scenario tool, you have to click on the ProMax ribbon at the top here and click on scenario tool. this will pop up this scenario 2 window. Make sure you give it a name. In this case, I've given it amine scenario study. And we can start inputting inputting the inputs and outputs. I only have one input, so I'm going to add a variable in the input. I'll first give it a name, MDEA weight percent. Now tell it where on ProMax it is. So I'm going to click on this. I'll see a very similar window over here. In this case, is the MDEA weight percent, which is controlled by this makeup block. So what that means is within the flow sheet called MDEA unit, but instead of a P stream, I'm looking at blocks. Under blocks, MDEA makeup, properties, target outlet composition, and the one I'm looking at is MDEA. I'll click on that. It'll bring me back here and have its location listed here. Next, where is it on Excel? I could type in an address here, or I could simply just highlight this and it'll automatically update the address accordingly. Last, I need to check my units. Percent makes sense. I'm not looking at ppm, I'm looking at percent. So with these 4 things input, I'm going to click OK. Now I have 2 outputs to set up. I'll be a bit quicker for these 2 because it's much of the same. I'll add variable, give it a name, sweet H2S, ppm. When I select ProMax object, instead of navigating through this, there's another fancy quality of life feature we have where you can actually click on the stream once to select it as such, and it'll bring you to the sweet gas, the location of the sweet gas within the tree. And it doesn't take much to go to the total composition, mole fraction, H2S. Next, where is it on Excel? I could re-highlight this, or I can use this directional pad over here to move my selection left and right. Then once I have the location I want to print the information in, I check my units, ppm, that's correct. I'll click OK. Last one, rich loading. I'm going to do a bit of the same, where I go to the flow sheet, look for where the rich loading is. I can right-click on it, copy it to the clipboard. Now I have it prepared in my clipboard. I can add, I'll name it rich loading. First thing. Second thing, where is it on ProMax? Instead of selecting a ProMax object, I can just put Control V to paste it. Click on enter, and it will automatically give you the location of it. So we have many ways of specifying this scenario 2 inputs and outputs. So it's up to personal preference which one you think you're faster at. Next, where is it on Excel? I'll use the directional pad again. And lastly, check the units. Rich loading is mole per mole, so there's no units. This makes sense. I'll click OK. And then make sure I'll run runs 1 to 6. I'll click run right here. So with this tool, you will notice a few things. Firstly, I'm still able to control the tool, and you can see what step you're in based on the colors that are flickering in and out. So blue ones show you outputs, yellow ones show you inputs. This is useful because sometimes you might have accidentally selected a wrong area, and then this will indicate to you, okay, which area it is. So if I start to see blue on this part, I know I specified something wrongly. Next thing, I can stop this anytime I want during the run. So if I, for example, I spot a mistake, the thing is not frozen. You can still interact with it. And you can click on stop at any time to stop at anywhere you want and troubleshoot. Next thing, if you ever want to know how the progress is going per iteration, it actually constantly updates within the Visio document itself, within ProMax itself. You can see the errors and stuff, and you can actually still interact with a lot of it. So I can still go to the solver summary to see which iteration it's currently at. So currently the recycle block's at iteration 3. I can If it solves, I can go into, for example, the makeup renaming. I can take a look at the flow rate and see how it varies. So a lot of it is still interactable even while it's running. And as you can see here, it's a very powerful tool because it combines the best of both worlds, where you have Excel features and you have ProMax features. Excel features are useful. For example, this graph you see right here that's plotting itself just takes the value here. You can make any graph you want and customize it however you like, having two axes, color coding it, adding these lines to show you where my specs are, etc., etc. And you are not limited by how many inputs and how many outputs you're using. You can have huge studies with hundreds of runs, maybe 10, 20 inputs and 50 outputs. We have used these kind of things to do sensitivity studies. So we can vary our flow rate by plus minus 10%, or vary our reboiler duty by plus minus 10%. And this will let us see how robust our system is in a very objective way. And for some of our clients, they have even opted to tie their historian with ProMax. So their historian will generate some will generate the plant data in an Excel format, and we can format this to run through all the plant data and then tell you how far off ideality or how far off a clean system you are. Doing it this way allows you to really plot control charts and have it have meaning, because you can compare the values with what it should be if you had a clean system. Okay, so in this case, the scenario 2 is complete. And I can see from here, my specifications, if you recall, rich loading 0.5 is typically the maximum we recommend. And the sweet gas is 8. You can see from here that once I drop my MDA strength below 44%, my sweet gas will be higher than 8. So that's a no-no. Rich loading, as I drop my MDA strength at about 45, it starts to go above 0.5, which means it'll be too corrosive. So I'm not going to have that. So comparing the two, I can now tell my boss, okay, when it starts to get close to 46 or 45, when I do my amine study, I should really start topping it up. Because unless I change something else in the plant, like increase the flow rate or do something else, I'm going to break my specifications or make a corrosive rich amine stream very quickly. Okay. So that concludes a very simple take on what a scenario 2 can do. It can do a lot more than this. If you have any ideas of studies you want done, email us after this webinar and we'll be happy to help you with that. Okay, let's move on to the last thing, user value sets. Okay. Now let's talk a bit about the most flexible feature on ProMax, user value sets. And this allows you to put in your own values into ProMax. And they are all enabled to interact with specifiers and solvers. This will allow you to do almost anything custom. We have used this to implement company costing procedures into a ProMax file. We have added correlations that companies use and even use this feature as a control panel with a bunch of if then else statements to change the mode of operation of a demethanizer from ethane recovery to ethane rejection. So it's a lot more powerful than what you might think it would be at a quick glance. Once again, I'm going to be very brief here. This is more for you to review after the webinar because we'll be sending these slides out. To access the user value set feature, you're going to have to click on the project viewer or double click on any object on ProMax. This will bring up a project viewer, and on the bottom left, you can look for this thing called user value sets. Right click on it and add a set. A set can contain as many user values as you want. and it helps you neatly organize different user values. So for example, you don't want all your SRU values to go into your amine values, for example. And each set over here, if you want to add a user value, you have to click on add at the bottom left corner here. Clicking that will bring up this dialog box. And the thing that's most important is grouped up at the top. And why is it important? Because when someone says the heat is 1000, does he mean watts, joules per hour, BTUs per second? It's very important that you have the units of whatever number you're looking at. The most flexible way of inputting your units is through the user-defined unit set. It allows you any combination of ProMax units and any number. You can make 500 times kg per 200 times meter cube times second, for example. Why you would want to use ProMax defined units is because we have unit conversions for every single one of those. So we'll show you more on this during the demonstration, but it will allow you to convert between units that you use. We also have a category for unrecognized units. This gives you units that maybe you can't find in ProMax, for example, dollar. However, because we do not recognize it, we wouldn't have the unit conversions enabled. Finally, we have standard units, and these are more for if you just want your own external value of something we already have. For example, ambient temperature, we already have temperature, but we don't really have anywhere for you to input ambient temperature. You can just pick it in as one of these default values. Since these are often tied with a calculator like a specifier, if you tick this box right here, it will automatically generate a specifier for you, and it will give it a name and everything. And finally, make sure you give it a name because you're going to have a few of these and you need to be able to differentiate them a bit. So let's move on to a quick demonstration before we go to Q&A. Okay, back to this model again. We'll be adding two user values here, but first we have to add a set. To add a set, I can go to Project Viewer. On the bottom left corner over here, I can see user value sets. I'll right click on it and click on add. I'll give the set a name, amine user values, for example. And I can add a new one. Let's add steam ratio. I'll show you why we're adding this in a bit, even though we technically already have it in the thing. I'll associate it with, oops, this should be kg per meter cube. That's the units, my apologies. And the name here is steam ratio. Okay, I'll click on associate with new specifier. This is because I'm going to create a calculator that tells me what my steam ratio is. So I'll click OK. As you can see here, a specifier is already created for me, so just double click on it. And now what do I want to do? So how do I calculate steam ratio? Is the amount of steam divided by the amine flow, right? So I have to make sure the units make sense. So my steam has to be a mass flow rate, kg, and my amine has to be a volumetric flow rate, meter cube. I'll just use my moniker location. So I'll double click on the steam. The mass flow rate is here. I'll just right click on it, copy it, go back, add, clipboard, steam. And now I've added my steam flow rate. Next, my lean amine flow rate. I'll double click on the lean amine. Flow rate's here, right click, copy, go back, and clipboard, amine. Okay. Now I have both of them, and it makes sense. My result is 130 exactly. This obviously makes sense because we actually have a specifier forcing it to be 130. Now, why do I want to put this here? Well, unlike in the calculator itself, which is over here, this text is not easily accessible. It's not in a neat little packaged location where you can easily access whatever this number is. In contrast, within the user values, over here, you can right click and copy the moniker. You can use this as a part of your results as in the scenario tool. You can now use this to connect with other specifiers, solvers, etc. This helps you organize everything very neatly. Additionally, if I drag out a property table, I can go to I can add this as a short moniker. I'll name it steam ratio. And under my property table, I can click on moniker and double click this. And now I can display my information on the flow sheet. This is a handy way if you don't want to do the mental math to figure out what this divided by this is. Okay, that's an example of a non-interactive user value, whereby whatever is here, it just reports a value, it does some calculation. Another example of its use is if you want to calculate maybe how much milligrams of SO2 you are emitting per normal meter cube of gas, and use that to calculate it. What about a more interactive value? So I'll return to my user value set, and I'll add in what I call target rich loading. Okay. I won't associate it with a new specifier because this is something I want to specify myself. And the unit, I'll leave it as blank because it's mole per mole, which cancels out. I'll click OK. Now over here, I'm going to make my target 0.45. I'm going to copy this. And now within this calculator, instead of putting 0.45 here, which I can't really interact with, I can click on add and add my own. I'll name this target RL. RL stands for rich loading. Click on add, and I can now replace this with target RL. So what you might be thinking, why is this useful? Very first obvious thing is now everything I want to specify that isn't a default property is all in one neat table over here. Secondly, now I can edit the value outside of the box. I can interact with this. And by interact with this, it means I can go to my scenario tool. And I can actually add the target rich loading here so that I can see maybe how much flow I need to maintain 0.45 rich loading or 0.47 rich loading when I change everything else. You can see how doing it this way, you can unlock a lot of different possibilities with combinations of these four very unique automation tools.